So, welcome back. We will continue discussion on Fourier transform of L1 functions, and in today's class we derive the Fourier inversion formula. So, in the previous class I gave a heuristic argument how this formula looks like, and today we will try to prove it in a rigorous manner. So, let me first state the theorem. Okay, so this is the Fourier inversion formula. So, suppose, so in this class and perhaps even in the next one, so I am working with Rn. So, all functions are defined on Rn, and integral again means integral over Rn. So, let me not repeat that. Okay. So, suppose f is in L1 function, and so its Fourier transform is defined, and suppose both are in L1. Okay. So, define. So, once f cap is in L1, so we can define this integral. So, 2 pi minus n by 2 integral f cap y e to the I x dot y. So, slightly differs from the Fourier transform. So, this is dy. Okay. So, if you compare the definition of the Fourier transform, this is nothing but the Fourier transform of the transform evaluated at minus x. Okay. So, we will just come to that in a point. Then f equal to f almost everywhere. So, this is the inversion formula we are looking for. Okay. So, similar to the properties of the Fourier transform, we already done. So, consequences, okay, let me just write them. We will come to the proof in a moment. So, we have already seen that. So, same argument works here. F is continuous and vanishes at infinity. And by our convention, I already discussed about this. So, we also say that we say f is continuous in this case, because f is equal almost everywhere to a continuous function. So, we say f is also continuous. So, this is just a convention. Okay. So, that is the first one. Okay. The second one, uniqueness. So, if f is in L1 and f cap is 0 almost everywhere, then f is 0 almost everywhere. So, sometimes one will not say this almost everywhere every time. So, f is always understood the equalities are in the sense of almost everywhere. Okay. So, that f cap equal to 0 means that f cap is in L1. So, we can apply the inversion formula and that is why we get f equal to 0. So, by linearity, so this means that if two L1 functions have if you consider two L1 functions f and g, and if we assume that f cap equal to g cap almost everywhere, then f is equal to g almost everywhere. So, there is uniqueness. So, this implies, so let me just write that. So, the Fourier transform as a linear transformation to L infinity. In fact, it is a this, if you consider the properties of the Fourier transform, okay, they form a subspace of L infinity, okay, so which are continuous and vanishing at infinity, is linear and 1 1. Continuous, of course, linear, continuous, so we always want that, and uniqueness is there. Okay. But however, till date we do not know what is the range of this mapping L1 to L infinity. Okay. But soon we will extend this concept of Fourier transform to L2, and there we know that it is an onto linear continuous operator. Okay. And one more thing, let me just again by using the Fourier inversion formula. So, we have this f x is equal to f cap minus x, and if you repeat it 2 more times, so we get, okay. So, let me write this instead of writing 4 hats. So, let me write that. Okay. So, under suitable conditions on f. Okay. So, this operator Fourier transform satisfies f4 is identity. So, I will come back to this when we extend this operation to L2, and then we will compute the eigenvalues and eigenfunctions. So, hope time permits for that. Okay. So, now to the proof of the inversion formula, some preparation. Okay, we will do some preparation. So, again these are facts from LP species. So, I will just list one by one preparation. Okay. So, recall the continuity of LP functions in the norm. Okay. So, what does this mean? So, here the range is less than infinity. So, if f is in LP in this range, then limit we will rephrase this. Okay. So, we have already seen this one. So, f of x plus h minus f x to the power p is 0. Okay. So, how do we rephrase this? So, for each y in Rn, define this shift function from, okay. So, define f of yx. So, this y is fixed. Okay. So, this is just f of x minus y. So, this of course, you can define it for any measurable function. So, this is just So refreshing refreshing of the continuity in the norm is this following. Okay. So then it is equivalent. Then you consider this mapping Fy. Okay. So if F is in LP, this is on also in LP. So this is a mapping from Rn to LP. So this is a metric space, this is a metric space, and so this is continuous. As I said, so many properties do not hold for p equal to infinity, so that you should check it separately. Okay. So this continuity of this map is equivalent to continuity of the continuity in the norm. Okay. So this is one thing, and now to the proper proof of that inversion formula. So we just let this phi lambda x mod x square by 2. There is nothing special about this function, it is only for the easy computation of things that follow. So if you look at closely the properties of these functions we use, so you see that there are many choices for such functions. Okay. So this is lambda positive. Okay. And we also seen that if I take lambda equal to 1, so that is just e to the mod x square by 2, and we have seen that its Fourier transform is itself, that we have seen. So that we are going to make use of it. So if you consider some other function that may not be easily computable, but if it satisfies the properties we want, then that is sufficient. Okay. And put psi lambda x 2 to the power 2 pi to the power minus n. So we will know in a moment why that constant we are choosing. So this is integral phi lambda y e to the I x dot y dy. Okay. So that's essentially Fourier transform of phi lambda. So we just compute once again. So just 2 to the power minus n by 2, one half part is taken here. So you get lambda to the minus n by 2 e exponential. So let me write that minus mod x square by 2 lambda. Those of you who have studied heat kernel, so it is heat kernel, and the role of T is played by lambda here. That is the only difference. So it is exactly the heat kernel if you have studied it. Okay. So the important properties we are going to use here. So this 0 strictly less than phi lambda x less than or equal to 1. Okay. And phi lambda x converges to 1 as pointwise. Okay. So that is one important property, and this constant, because of this constant, the integral psi lambda is also non-negative, but this important thing is it is 1, and that is where this constant is chosen, and psi lambda of course greater than or equal to 0. Okay. So with this preparation, so we will just so I will write some numbers here, proposition 1. So it's only these numbers are used only in this lecture. Okay. So if G is an L1 function, then so I compute this convolution G star psi lambda x is equal to 2 pi minus n by 2 integral. So this is nothing but phi minus y square by 2 g cap y e to the I x dot y dy. Okay. So this is just computed. You have to write what this. So write the expression for this thing. Write the formula for the convolution and substitute for psi lambda. Substitute. So that's another integral. Substitute for psi lambda and then use Fubini and interchange the integrals. So use Fubini and interchange the integral. So that's very straightforward. So there is nothing much to do, but important again is regarding the consequences. So essentially we want to take the limit of this convolution as lambda tends to 0, and we observe two possibilities. Okay. So if g cap is in L1, then the absolute value of the integrand is less than or equal to mod g cap, and that is in L1. So we can use dominated convergence. So dominated convergence implies limit g star psi lambda x as lambda tends to 0 is equal, and the integrand converges to g cap y e to the I x dot y as lambda tends to 0. Okay, so that's so 2 g cap y e to the I x dot. So we are already seeing the terms we want. The second choice is if g cap is non-negative. Okay. Just look at the again integrand, and for what you don't want this oscillatory term, so put x equal to 0 there, so that's gone. So then integrand is non-negative and it's monotonically increasing as lambda decreases to 0. Okay. If g cap is non-negative, then the monotone convergence theorem implies limit g star psi lambda at 0, because we don't want that oscillatory term. So lambda tends to 0 is again 2 pi n minus by 2 g cap y dy. Okay, so these two things we use later. Okay. So, second proposition, okay. So, suppose G is bounded function and continuous at x, then again the same limit. So, limit G star psi lambda x is G of x. Okay. So, again proof is very simple, just let me write that. So, here we are using the property of psi lambda that its integral is 1 and it is non-negative. Okay. So, you just compute the difference. Gx sorry integral g of x minus y, that is coming from the convolution, this is minus gx. So, this is minus gx and psi lambda y dy. So, here we are using the property that integral of psi lambda is 1. Okay. So, that is we could write that gx term as gx into the integral of psi lambda and I take just gx inside. Okay. So, just recall, so this is some constant that lambda to the minus n by 2. So, exponential minus mod y square by 2 lambda. Okay. So, now you just change of variable. So, y by root lambda you keep eta. So, this change of variable gives us integral g of x minus root lambda into n minus gx, it's that constant is there, okay, e to the minus eta square by 2 d eta. So, these lambda factors disappear after we change this, make change of variables. Okay, again look at the integral. So, by our assumption g is bounded, so this is less than or equal to, in absolute value of course, twice the g infinity e to the minus mod eta square by 2, and that is in L1. And what happens to the integrand as lambda tends to 0, and the integral tends to 0 as lambda tends to 0 by continuity of g at x. Okay. So, these are hypotheses. So, again you just use the dominated convergence theorem. Okay. That implies the proof. So, proof is complete. Okay. So, one more proposition which is very similar to the mollifiers we did. Okay, so, again this is, we can state it for all this p but just to use it for p equal to 1 and 2. Okay. For 1 less than or equal to p less than infinity, if f is in LP, so f star psi convolution psi lambda is also LP for all lambda positive. Okay. And so this is important. So we have this estimates FP and minus F p tends to 0 as lambda tends to. This is exactly, the proof is exactly same as we did it in modifier case. Okay. Only thing here is the psi lambdas do not have compact support, but they are non-negative and integral is 1. That is all essentially used. Okay. So in general, okay, this is again a fact from measure and integration. So if a sequence converges to, since we are talking, so if a sequence Fn converges to F in the norm, it may not converge to the function almost everywhere, but there is a result, so it is attributed to Weil, so it is called Weil's lemma. A subsequence converges to the function almost everywhere. Okay. So let me just state that there exists a sequence lambda n positive reals converging to 0 such that if you take these convolutions f star psi lambda n and that converges to F almost everywhere. Okay. Fine. So with this preparation, now we come to the proof of the inversion formula. So let me just give that proof. Okay. So proof of inversion formula. Okay. So since f cap is in L1 by assumption, since since f cap, f and f cap, okay, both are there in L1, by proposition 1, okay, we have f star psi lambda x converges to that 2 pi minus n by 2 integral f cap y a to the I x dot y. Okay. So as lambda tends to 0. Okay. So this is from proposition 1, and by proposition 3 along a subsequence. Okay. So this along a subsequence lambda n converging to 0, this we have fx. And this is precisely, this is what we have defined in the statement of the theorem, Fourier inversion formula. Okay, so this converges to big f of x for any sequence converging to 0, and this is only along a subsequence, but limit should be the same, and that implies f equal to f almost every. And that's what we wanted to prove. Okay. So far, because of that integral, we have been able to define the Fourier transform only for L1 functions, and whether it is possible to define for other LP functions or not. So that is the next discussion. Okay. So this let me just begin with, and hopefully will complete also, extension to L2. So extension of the Fourier transform. Okay. So let us begin with a theorem. So this is the first step and crux of the matter. Okay. So if f is in L1 intersection L2. Okay. So if f is in L1, we can define its Fourier transform, no no problem. So what this extra assumption tells about the Fourier transform? Then, so we certainly know that f cap is a bounded function, but in this case f cap is also in L2. Okay. So this extra information we are getting from this assumption, and not only that, and norm of f in L2 is same as, and for this equally to occur, the choice of that constant 2 pi to the minus n by 2 is important in the definition, otherwise that constant pops up here. This okay. So this is called Parseval's relation. So this is an important relation that will enable us to extend the definition of Fourier transform to L2. Okay. So since all the preparation is done, so just again we are going to use proposition 1, 2, 3 here. Okay. Just in order to see this. Okay. So I will just take few minutes and complete the proof. Okay. So define f tilde of x is f of minus x conjugate. So if again if f is real valued, so it is only f of minus x. Okay. You are just changing the sign of the argument. Okay. And so again f tilde is in L1, so no doubt about that, and so you define this. So since both f and f tilde are in L1, so and the g is nothing but the convolution, so g is also in L1. Okay. So I just leave it as an exercise. This is just again a simple application of Fubini theorem. Okay. So again this constant pops up here, because we have not included the constant in the definition of the convolution. only in the Fourier transform. So this f cap j, so this is just multiplication of functions j, and again it's very easy to compute. This argument change is only here, so you just get 2 pi minus n by 2 f cap j mod square. So it's non-negative. Okay, so the Fourier transform of, so this is just an application of Fubini theorem. So this is generally true. If you take two L1 functions, then the Fourier transform of their convolution is the product of the Fourier transforms putting this factor. Okay, it's very straightforward. Apply Fubini's theorem. Okay, so this so now recall again proposition 1, 2. Okay, so that's what we are going to use, proposition 1, 2. So proposition 1. So what does that say? So now we want to apply that to G. Okay, so G star psi lambda 0, because now in this case G cap is non-negative. Okay, so I can apply that one of the conclusions. So by monotone convergence theorem, this goes to there is this. Okay, this is plus. Okay, okay, so just keep track of those power, so you get exactly just integral f cap j square. So we might try to extend the definition of the Fourier transform to L1 functions, and in this direction let me start with this theorem. So if f is in L1 intersection L2, then f cap is in L2, and the L2 norm of f is same as L2 norm of its Fourier transform, and this is called Parseval relation, and this is an important step in extension of the Fourier transform to L1 functions. Okay, so proof is already done in the sense that all preparation is done. So you have to just only apply proposition 1 and 2. Okay, so you start with this definition, f tilde x is f of minus x conjugate. So if f is real valued, so we can remove that thing, and g is the convolution of f and f tilde. So a simple computation shows that, so g is of course in L1 and g cap is this non-negative function 2 pi to the n by 2 mod f cap j square. So we can apply proposition 1 to conclude this. Okay, so this proposition 1 implies, and this just follows from the monotone convergence theorem. So on the other hand, just look at here. So now we again compute this g. Since g is in L1, we also have this, right, and g cap is in L1, because g is the convolution of two L1 functions. We already know that g is also g is in L1 and okay, that will leave it. Okay. So now gx is the convolution of f and f tilde. So let me write that very definition. Okay, so this is f of minus y bar dy. So this is just definition of the convolution. Okay, so you again change y to minus y, so you get f of x plus y fy bar dy. And since we are assuming f is in L2, so let me write this as the inner product of f minus x. So we have introduced this notation with f. Okay, so this is L2 inner product. Okay, so this is where we are using the other hypothesis that f is also in L2. Okay. So now we know that, so by continuity of inner product, this is true in any Hilbert space, and continuity of this function. So y going to fy, we are using it in L2. So we conclude that, so this is important, so G is continuous. Okay, further by Schwarz inequality, so in fact we have to attach Cauchy name also, Bunyakovsky. So in a general setup this is called Cauchy-Schwarz Bunyakovsky inequality. Okay, so we have this. So G is bounded. So G is bounded and continuous, and again now you apply proposition 2 implies G star psi lambda. We are interested only in 0 because we already computed this limit at 0. So this is just at 0 converges to G of 0 as lambda tends to 0. But what is G of 0? G of 0, just you put x equal to 0 there, so f of minus y, and it's precisely you get f 2 square. Okay, but we have seen this one as already integral f cap j square. Okay, so that implies, so that's what we want. So f cap is in L2 and this. Okay. So this is the crux of the matter, and now the extension becomes very straightforward. So that we will take up in the next class. Thank you.